So here we're going to see the gradient work in a couple of other applications. First thing is, you know that if you have a level curve, let's say you've got a level curve that looks like this, and you pick some point AB on that level curve, and you look at the vector that's tangent, it goes this way. Well, it turns out that the vector is perpendicular to the gradient. So if that is AB going that way, then going in this direction is your gradient evaluated at AB. So the gradient and the tangent are orthogonal to each other. So my theorem that I wrote down the bottom here, well, it's not my theorem, I didn't come up with it, is that given a function that's differentiable at a point, the line tangent to the level curve is orthogonal to the gradient as long as the gradient is not 0. So those two things are orthogonal to each other, which means that their dot product should be 0. All right, let's take a look at a couple of examples, or at least one example. Here I've got an example. F of xy equals negative 4 plus 6x squared plus 3y squared at the point negative 1, negative 2. All right. What do I want to do? I want to find the level curve for z at that point. I want to find the vector that gives the direction of maximum increase, decrease, and no change, and a line tangent to the level curve. And I put a formula down the bottom that we will come back to when we get there. So the first thing is, I want to find out what is the z value at that point. I have an x value and a y value. I don't have a z value. So if I take negative 4 plus 6 times negative 1 squared plus 3 times negative 2 squared, I get negative 4 plus 6 plus 12 equals 14. So that's my z value, which means that at the point 1, 2, negative 1, negative 2, the z value is 14. So I have a point, negative 1, negative 2, and now I can fill it in with 14. Great. Now let's see what those level curves look like at z sub 0 equals 14. The original function, I'll put a 14 on the left side. I was given negative 4 plus 6x squared plus 3y squared. All right, so a little bit of solving, add a 4 to both sides, so I get 18 equals 6x squared plus 3y squared. All right, good, the numbers work out nicely. If I have both an x squared and a y squared with a plus in between them, it's going to be an ellipse. So this is going to give me 1 equals x squared over 3 plus y squared over 6. Okay, it's an ellipse. The y values are the higher ones, so it goes up to plus and minus the square root of 6 this way, goes to plus and minus square root of 3 that way. All right, there's my ellipse. Not a fantastic ellipse, but it's an ellipse. All right, the next question asked about maximum increase, maximum decrease, and no change. Well, for that, we need the gradient. So our original function, again, was negative 4 plus 6x squared plus 3y squared, and that was our f of xy. So the gradient must be the partial with respect to x, so I'm going to get a 12x, partial with respect to y, 6y. All right, now evaluate that gradient at the point I was given as the first two coordinates in here, negative 1, negative 2. 12 times negative 1 is negative 12. 6 times negative 2 is also negative 12. All right, if you see something like this, can you jump to the fact that the unit vector then must happen to be 1 over the square root of 2, 1 over the square root of 2? Negative 12 is just down in the third quadrant going that way. So the direction of maximum increase is the same direction as the gradient. So it's going to be negative 1 over the square root of 2, negative 1 over the square root of 2. Maximum decrease will then be the opposite. So positive 1 over the square root of 2, positive 1 over the square root of 2. And then can you see no change? Yeah, I'm going to flip them, but if it's a 45-degree angle, flipping them isn't going to make any difference. So I just have to negate one of them. So negative 1 over the square root of 2 positive 1 over the square root of 2. All right, the last thing it asked me to do was to use the formula down the bottom to find the equation for the line that was tangent at that point. So let's try that. Let's use the formula that was given to find the equation of the line that's tangent at that point. It's got a partial y times y minus y1 and a partial x times x minus x1. Let's go back for a second and look at the gradient. The gradient of f at xy is 12x, 6y. So now I need to evaluate that at the point -1, -2, which I actually already did. The gradient of f evaluated at -1, -2 is going to be -12, -12. Sometimes you'll also see that, by the way, written as like a 6y, right, that partial f with respect to y. You could also write as a 6y and then draw one of those bars and then write -1, -2 to show you're evaluating it at that point. So now that we have the values for the partial f with respect to x and y, we can just throw them in. So I get a -12, and then y minus, my y1 is this -2 that's up here. So y minus a -2 gives me y plus 2. Then minus 12, because that's my partial f with respect to x, times x minus a -1. All right, I can actually divide everything through by -12 so that I get y plus 2 plus x plus 1 is equal to 0. That gives me y equals, move the x over to the other side, and I get -x. Move the 3 to the other side, and I get -3. And that's the equation for the tangent to the level curve. Remember, if we're doing level curves, we're in terms of x's and y's on the xy plane. Right, for the next one, let's take a look at a paraboloid. In this case, I've got an f of xy that was given, 0.80 on a level curve, verify that the tangent line is orthogonal to the gradient. If I evaluate that function at 80, I want to get some value for z. It won't be surprising, but let's do it anyway. If I put in a 16, I'll get 16 minus 8 squared is 64. And then 0 over 16 is 0. 64 over 4 is also 16, so I just get 0. So then find the level curve z sub 0 equals f of xy. Well, z sub 0 is 0, so we're going to import our answer in there, and we're going to get 0 equals 16 minus x squared over 4 minus y squared over 16. Move those over to the other side, and you'll end up with x squared over 4 plus y squared over 16 is equal to 16. Divide both sides by 16 and see what you get. 4 times 16 is 64, so I get x squared over 64. 16 times 16 is 256 equals 1. So this thing here is the equation for the level curve at z sub 0 equals 0. It's an ellipse. It's an ellipse that is twice as tall as it is wide. All right, so now we need the gradient. For the gradient, we need partial derivatives. So the partial derivative of f with respect to x is going to be a -2x over 4. And the partial derivative of f with respect to y is going to give me a -2y over 16. And the point that I have is 80. So now I can move this over. This means that the gradient of f at xy is -x over 2 if I simplify the first term, -y over 8 if I simplify the second. Right, now let's evaluate that gradient at the point that I was given, which is 80. So now I get -8 over 2 and 0. Okay, simplify that. The gradient is -40. Right, can I find the slope of that curve, that level curve, implicitly? So if I know what the gradient is, I know the partial f with respect to x, I know the partial f with respect to y. So let's find the slope of the level curve. Remember the formula for implicit differentiation was opposite of partial f with respect to x over partial f with respect to y. So partial f with respect to x is x over 2. I'm going to change the sign to make it positive x over 2. On the bottom, I'll have a negative y over 8. All right, let's clear out our fractions here. Let's hit the top and bottom with an 8. So that will give me a 4x on the top and a negative y on the bottom. That is the slope of that level curve. Now, we were given it at the point 80. So what happens at the point 80? If I put a 0 down here, this thing is undefined. Which must mean then that the tangent line is vertical. If the slope is undefined, then the tangent line is vertical. What if I were to graph this? Remember we had said that here we are, the x-intercepts were 8 and negative 8. The y-intercepts were 16 and negative 16. What does that look like if I go to graph it? 8 and negative 8. And then 16 and negative 16. Can you see that if I graph even the right half of this ellipse, at the point 80, I got a vertical tangent. And so the tangent line is vertical. How about the gradient at 80? If I look at the gradient at 80, the gradient at 80 is given right here. Negative 40. So the tangent line is vertical. It turns out that the gradient is horizontal, right? Where does negative 40 go? It goes that way, 4 units in the negative x direction. So the gradient and the tangent line are vertical. If you want, you can take the dot product, and you should get 0. All right, a couple of quick things left here. This time we're going to look at the question about a plane. I've got the plane f of xy equals x plus y, the path of steepest descent starting at the point 2, 2, 4. Well, the first thing I'm going to do is find the gradient. This is starting to sound like a common procedure. When in doubt, find the gradient. Just like in Calc 1 at the beginning when you weren't sure what to do, you always found the first derivative. Well, here, you're going to do essentially the same thing. Find the gradient. So the gradient is going to be the partial derivative with respect to x, which is just 1. Partial with respect to y is also 1. So if you want the steepest descent, then you want it in the direction of negative 1, negative 1. Now for the equation of a line, remember how we find the equation for a line? We've got our r sub 0 plus vt, where v is that direction vector. Well, that direction vector you just found. Right? My original point then was 2, 2, right? Because I'm operating on a plane. So 2, 2 plus my v, negative 1, negative 1, times t. All right, so now let's look at what this gives us. We end up with a 2 minus t for the first coordinate, and, boringly enough, a 2 minus t for the second coordinate. If I want to write this out in terms of x's, I can do that. I can write this out as x equals 2 minus t and y equals 2 minus t. So in other words, if I placed a ball on there and started at, let's say, t greater than or equal to 0, it would go in that direction. It'll roll down the plane in that path, where x equals 2 minus t and y equals 2 minus t. All right, and the only other thing to mention then is, what do gradients look like in 3 dimensions? Well, I said instead of level curves, they have level surfaces. So you're going to peel these things away. Instead of taking the level curves and stacking them on top of each other, you're going to end up peeling level surfaces away like an onion. Not called that because they make you cry, just because they happen to be built one on top of the other on top of the other. You can define the gradient then in 3 dimensions. Partial with respect to x, partial with respect to y, partial with respect to z. And again, your direction vector would then have u1, u2, u3. And your directional derivative would still be the dot product of the gradient and that unit vector that gives you the direction. Good. And that's the end of part 2.